Boom. Hello and welcome back to Calculus 1 Saturday edition. Right, we have 4.2 section that in the book is called What Derivative Tells Us or something like that. I renamed that into first and second derivative test because that's what we do in this section. We learn about second and first and second derivative tests that are used to determine the intervals for increase, decrease, concavities, and then we also bring back min, max, we bring back critical points, we bring back inflection points, and so on. So a lot of cool things. So let's first talk about just in general shape of functions and things like that. So I'm going to talk about x squared and x cubed at first. So this is x squared and this is x cubed. We should know those shapes. Now, if you look at these two functions, so f of x equal to and g of x equal to, for the x squared, we clearly see a critical point in the bottom. We know it's the absolute min. And we calculated this so many times. The first derivative is 2x equal to 0, x equals 0, and then finally 0, 0. And we know it's a critical point. It worked out to be minimum. I think this is the third time I'm doing this calculation, right, in the last hour. But now we're going to do the same thing for our x cubed function, and right, the scary thing happens. We have 3x squared, you set it equal to 0, you get x equal to 0, and you get 0, 0 on a critical point. And then you look at your 0, 0, and it's not a min, and it's not a max. And don't worry, the world is not going to end because of that. We have the third creature called an inflection point, and we are going to learn about that one in this section. So what are the things that we are learning now? We are going to learn that this blue part of x squared is the decrease, and we are going to learn that this green part here is the increase. And we are going to see over here that the entire function is increasing all the time. So for us to have min or a max, decrease has to change into increase or increase has to change into decrease. Like that has to be required. Otherwise you don't have min or max. So we see that this critical point over here did not give us the change from increase to decrease. Now, is increase, decrease important? Right? And I should talk primarily now to business people and economics people in this classroom. Right? Sure, physics, engineering, STEM, yeah. Clearly it's important, right? But let's pick on business now since we started talking about business. Right? So, let's take a look at my favorite company to hate. All right. So, is it time to panic? Right? So, if you're looking at the graph, are we supposed to panic? Is it supposed to be sell, 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 sell? Or we're just going to be just fine, all right? This was yesterday. It's closed today. You see that? It's green, right? It's not sell, sell, sell. But what do you see over here? But then, that's a 168, that's 172. It was, fluctuating in there. It actually pretty much closed where it started. So, it was just a wash day. Just a wash. Nothing special. Boom. 5 days. This was the whole week, Monday through Friday. You see, increase, decrease becomes important for analyzing these kind of things. Right? You don't know what's going to happen next Monday, but if it's going to go to 0, you're just going to lose. No, I'm serious, right? You guys don't know, but these people will go, what is he doing? Is there another one over there? Oh no, there are 2 over there. But they're not paying attention. He's like, look at me! But the other 2 are like, they're actually looking away to the building. I had some baby one over there. Oh, come on. I can't teach. Go look at it. I mean, how can you teach with that thing? He goes like this. Watch it now, like, puts the wings together. As soon as you walk over, he goes, yeah, I know. I'm not joking. Like, why?
Oh my God, that's so good.
I know, but there are 2 others, right? You see the other 2? So I guess he's putting up a show for them, but they don't care. So, there, let's go with those cell phones, take the pictures. You don't have to go to, now he's posing. Look at me. Actually, I'm going to take pictures too, aren't I? Class is paused because of the vulture. That's the
majestic creature.
Majestic creature. I know, I just said it.
One time,
I've never seen it.
Somebody just pulled out that vulture.
Why's to get the other one?
Yeah.
Oh, it's fine. I'm so making meme out of this one. Yo, look at me.
You should put that in the course description. It's like, we're going to do calculus, but we got some bird watching in this as well.
Bird watching, yes. Bird watching 151, all right? All right, so your bird watching class 151 is going to resume now. We're talking about increase, decrease, first derivative test. So we're looking at this stock, right? And we see that on Monday, it started at 168, and it ended at around 168. So all of this up and down was a wash at the end. But, you know, some people at this point were going, yes, yes, go up, go up, go up. Oh, please go up. Please, 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 thank you, thank you, thank you. Oh, right? So you can't really follow all of these things. When you do investments, right, this is the stuff where you have to really pay attention. So it's a 1 month, 3 months, 1 year, 5 years. So when you buy a stock at $60, right, and then you wait 4 years for it to go to $160. So that's $100 per share. If you bought 1,000 shares, then you have $100,000 in those shares. It's a very simple math. So you buy 1,000 shares at 60, right? And then, or 100 shares at 60, right, at $6,000. That's the investment money, right? You give that, they take that, and then they go and they, buy other people's ideas and things, market them as their own, obviously. and then make money off of it. So that's that. And we want to see this type of a rise. So you go and you look at the trend and you say, okay, it's increasing for the first, 2 years, then it's decreasing for 2 years, then it's increasing for 2 years. And look at what I said, increasing for 2 years, decrease for 2 years, increase for 2 years. I only gave you the x coordinate because x is in years. So I wasn't paying attention how much it increased. It's just the trend. So when I take, this is first 3 years, you take the first 3 years over here, right? And you see that in these 3 years, 3 years, right? For these 3 years, there was an increase because it's going up. And then over here, we have a year of going down, actually. And then we have 2 years of going up again. So you will only list these intervals by looking at the x values. Every interval is going to be x1, x2. So 3 years, or 1 year, 2 years, so. So let's take a look at this type of analysis for our problems, and then we will eventually hit the inflection point, and then in the second derivative, and we will also going to look at concavity. The first graph that you see, which is the x squared graph, is concave up. It holds the water. And then the other graph, that 0, 0 is inflection point, which is a change in concavity. So the first part is concave down and the other part is concave up. And we'll deal with those things as we go. But let's take care of the first derivative first. First derivative test. And I'm immediately going to write the rules for it. This is the procedure that you must memorize. So it says, if f prime of c is larger than 0 on some open interval a, b, then f of x is increasing on a, b. So that's the rule. And the second part, if f prime of c is less than 0 on interval ab, then f of x is decreasing on ab. And that's that. This is your first derivative test. There is also the part, if you would, I hope you wouldn't ask, because we just had the lecture on it. If f prime of c is equal to 0, it's just a critical point. There's no interval there. It's a single point. So let's immediately take a look again at x squared. So f of x is equal to x squared. We are learning the procedure for first derivative on a familiar function. So, for the fourth time. So let's take the derivative. We have to find the critical points, right? So it's a 2x equal to 0, divide by 2, x equals 0, and we know the critical point is at 0, 0. Now here's your first derivative test done. What we do is we take all critical points and all vertical asymptotes and we partition the domain of the function. So I have a 0, that's negative infinity on this side, it's positive infinity because the domain for the x, right, squared is like that. So this over here is the critical point. I don't have any vertical asymptotes, so this is the only thing that is partitioning. Now what I do is I pick test points. One in each interval. So this is 0, critical point, is partitioning entire domain from negative infinity to 0 and 0 to infinity. And then I pick any number in each of those two intervals. I picked negative 1 and 1 because I'm lazy, it's easy to compute. If you like pain, sure, e minus pi squared will work just as fine. All right? So here's the first derivative test. I say f prime of negative 1. You see, I put the test point in the first derivative, hence first derivative test. Right? Words. So I'm placing the first, the test point in the first derivative, and I'm just going to compute. Now, first derivative is 2x, so I have 2 times negative 1, and that gives me negative 2. That's less than 0. So now, I am fixing my graph over here. Look what happens. I have a decreasing function up to x equals 0. So I put this arrow that goes downwards to the right. Then I go and I compute f prime at positive 1. This is the other test point. And I get 2 times 1, which is 2. And that's larger than 0. And that goes this way. Do you see immediately the way these arrows point that you do have a minimum at 0? Do we see that? There's a minimum at 0. It's a critical point, and the graph shows us it's a minimum. Put the green arrow here. It's a minimum. Because it went down and then it went up. That's a min. I don't have to know what the graph looks like. I see it from the diagram. I use the first derivative test to place those arrows, and arrows point the right way. Let's take a look at another example. What should we use? How about y equals 1 over x. Okay, so the derivative is negative 1 over x squared. Set that equal to 0. And we get negative 1 does not equal 0, no solution. Now, what do we know if it's no solution? No solution means no critical points, and that means no min-max. So do I do first derivative test? Yes, I can always do first derivative test because I have the first derivative and I also have vertical asymptote to partition. Even if I had nothing to partition with, the entire domain is just one partition and you can find the function going up or down on the entire partition. We'll do that as well. But see this one over here, for my first derivative test, I have no CP but VA x equals 0. So I can still do partition. Okay, let's do the partition. You just break it at 0, and you have your negative infinity, positive infinity. Get your test points. All right, negative 1 and 1. That's cool. And then we go f prime of negative 1. That's the first derivative test. You are plugging in test point in the first derivative. What do we get? We get negative 1 divided by negative 1 squared. And that's negative 1 less than 0. We have a decrease. Okay. F prime f1 is negative 1 of 1 squared, which is also negative 1, which is also less than 0. And this is also a decrease. Do we see from the diagram that there is no min or a max without even knowing this? We do. Because the max occurs when you have this situation, and the min occurs when you have this situation. And that's not the situation we have. Right? Now, luckily we know what 1 over x looks like, so we can quickly just visually confirm that. Because we are going to draw this piece and draw this piece for 1 over x, and then we see it's decreasing, right? This part is decreasing from negative infinity to 0, and then the other part is decreasing as well. Awesome. It works 100% of the time. So eventually I'm going to pick some of the problems from the book, but I want first to get these basic examples out. Now, we can go and do x cubed. Let's go with x cubed minus 1 or something. So it's just a little bit different, you know. X cubed minus 1. Take the first derivative. We get 3x squared. Set it equal to 0, and we eventually get x equals 0. And when you plug everything in, you get 0, negative 1 for critical point. And that's it. There are no other points. It's just one critical point, 0, negative 1. So now, first derivative test. We immediately draw the partition. We are again partitioning in 0. This is really boring, but sorry. We'll get different examples. So we are partitioning 0. There are no vertical asymptotes, so I don't have to add that in. And now I pick two test points. Again, negative 1 and 1. So f prime at negative 1 is 3 times x squared, which is negative 1 squared. And that is 3. Larger than 0, I have increase. First derivative test computed at 1 is 3 times 1 squared, which is 3. Also larger than 0. Also increasing. So you see from this calculation that the critical point you have is not min, not max, because of the arrangement that the chart gives us. Now we also know what the function looks like, so clearly, right, no max, no min if you look at the function. So no max, no min. Y equals sine. Let's go with sine. I want to do sine 3x, but let's do sine 2x. Where? Sine 2x. And let's restrict this on 0 to, let's say, pi. This is for you guys who love trig. Of course. So what do? Well, standard procedure. Critical points first. So y equals, the derivative of sine is, very good, and we also have 2 in front from the chain rule. Set this thing equal to 0. We have to solve cosine 2x equals 0. There are many ways in which you can solve this question. My preferred way is to draw the graph of cosine 2x and look at the graph. But then there are other ways with the substitution. For instance, you can make cosine theta equals 0, solve that, and then say theta equals 2x, and then, well, let's do it that way. Since you already have the graphical solution from previous time I did trig, let's go and say, so let theta be 2x. So now you are solving cosine theta is equal to 0. And then what we do is we know that the theta solutions are pi over 2 and 3 pi over 2. But I'm sorry, no one cares about thetas, all right? We want to calculate x's. So you substitute 2x for theta. And then multiply both sides by a half to cancel this. So x is pi over 4 and x is 3 pi over 4. See that? That's now 2 out of 4 solutions. There are 2 more because your period is now twice as short. The function oscillates faster. So, oh no, we cut it off at pi. That's fine. So we're done. 2 solutions only. Yeah. If this was 0 to 2 pi, you would have additional 2. But it's 0 to pi. I forgot that I cut it off there. Okay, so we only have 2 solutions. And now you will plug these guys back in the original function, y. So what's y of pi over 4? It's going to be sine of 2 times pi over 4, which is sine of pi over 2, so that's 1. And over here, y of 3 pi over 4 is sine of 2 times 3 pi over 4. That's 3 pi over 2. That's negative 1. So 3 pi over 4 and negative 1. So these are the values that we are using for partition. We are not going to have any vertical asymptotes because it's a sine function. Right? If it's a tangent function, you have to worry about that. But sine and cosines, they do not have any vertical asymptotes. So we are going to do that, and then let's do the first derivative test. Partition. Now I have 2 critical points to worry about. Pi over 4, 3 pi over 4. So pi over 4 and 3 pi over 4. On this end I have 0. On this end I have pi because it's the problem that cut off. We need to pick test points. So what's a number between 0 and pi over 4 that we can use? Well, hopefully pi over 8, because that's halfway in between. 3 pi over 4, pi and 3 pi over 4, right, have 2 pi over 4 in between. Well, that's pi over 2 as a test point. And over here, 3 pi over 8 again. Right, you can average, right, add those if you want to. So that will be 4. No, it's not 3 pi over 8. 7 pi over 8, yes, thank you. 7 pi over 8. 7, 7, 7, 7, 7. 3 pi over 8 is here. All right. So I have 3 partitions, 3 regions, because the 2 points, 2 critical points that we found are cutting the domain into 3 parts. Right? So now we compute first derivative at each one of these points. So the first derivative computed at pi over 8. Before you freak out, right, because pi over 8, you realize that you're going to be multiplying by 2, which cancels it into a quarter, so we're all good. So 2 times cosine of 2 times pi over 8. Well, that is 2 times cosine of pi over 4. Cosine of pi over 4 is root 2 over 2. So the whole thing is positive root 2. We have the increase on the first partition. Function is increasing. Calculate again for the next test point. F prime of pi over 2. 2 cosine of 2 times pi over 2. Cosine of pi is negative 1. 2 times negative 1 is negative 2, less than 0. Decrease. By the definition we started this section with. Right? We said if the derivative is less than 0, it's decrease. If the derivative is larger than 0, it's increase. So we calculated the second one. Now we know it oscillates, so the next one needs to be up. But let's calculate and show. The last calculation, f prime at 7 pi over 8. And that, and that is 2 times cosine of 2 times 7 pi over 8. Now these guys cancel, so you have 2 times cosine of 7 pi over 4. Right? Now where is 7 pi over 4? Because we have to use that. All students take calculus stuff, right? All students take calculus. So this is where the sines and cosines are positive or negative. So where is 7 pi over 4 on the unit circle? We just count. 0 pi over 4, 1 pi over 4, 2, 3, 4, 5, 6, 7. It's right here. Right, that's where it is. So this is 7 pi over 4. It falls in a fourth quadrant. Cosine is positive in a fourth quadrant. So it's 2 times root 2 over 2, which is root 2, which is bigger than 0. And there is another increase over here. Okay, good. Now we go back to the chart. Up, down, that's a max over here. And then down, up, that's the min over here. For the graph of sine 2x. Now you can actually graph this knowing this information. Because what do we have? We have 2, 3. So this is in fours now. This is pi over 4. This is pi over 2. This is 3 pi over 4. So pi over 4 and 1 is here. And 3 pi over 4 and negative 1 is there. Yay. It's just a regular sign that is squished. That's that. One more example of this and we can go to the second derivative test, which is the same thing as the first one. I mean, same procedure as a different. So let's find, ooh, you know what I forgot? Eesh. Now I feel, I'm sad now. I forgot to write the most important thing every time. Intervals of increase, decrease. This is like your answer to the question. So you have to write, right? You look at the chart over here and you say function is increasing. So f of x is increasing on, and then you have what? 0 to pi over 4. Union, what is the other one? 3 pi over 4 to pi. F of x is decreasing on pi over 4 to 3 pi over 4. This over here is the answer to the question, because what we are doing with the first derivative test is we are looking what are the intervals for increase and decrease. That's why I showed you the stock chart, graph, whatever, right? We were interested for how many years the stock is doing well, how many years it was going down, right? Increasing, decreasing. So all of this work we did, everything here, that's partial credit. Your answer are these two lines. This is the answer to the question. So note, somehow put the notes in your notes. Right, indicate that in your notes. English. This is the answer. You clearly stating that the function is increasing on these parts of the domain and the function is decreasing on this part of the domain. I missed it. So now we have to go back to every single problem we had before and actually write the answer. I didn't write the answer for any of the questions I did before. So here we go. I go back over here. And I have to say f of x is increasing on negative infinity to infinity. It's increasing on the entire domain. That's the answer. And if you draw x cubed, you know it's increasing everywhere because, yeah, there it is. Right, that's x cubed. Let's take a look at the previous example. Aha! The 1 over x. This one is always decreasing. So you would say f of x is decreasing on negative infinity to 0, union 0 to infinity. We have a vertical asymptote. That breaks the domain. Right? Function is not defined at 0. So for 1 over x, we have to add, this is the answer. Answer to the question, list the intervals on which function is increasing or decreasing. That's the first derivative test. Here we go for the x squared. So f of x is decreasing on negative infinity to 0. F of x is increasing on 0 to infinity. That's the answer right there. So find the intervals of increase and decrease for a given function. That's what you do. First derivative test. So I want to do one more example of the first derivative test. This one is quick. It's e to the x. Let's do ln. We did e last time. So y equal ln x. There we go. So what is my derivative? dy dx. It is 1 over x. We set that equal to 0. 1 is not the same as 0. No solution, meaning no CP, meaning no min-max. But I can still test for increase-decrease. Right? I can just draw a straight line like this, and this has no min and max, but it's increasing. So we have to worry about that. So let's do the first derivative test. And we have nothing to partition with. There is a vertical asymptote at 0, but that's like the end point, right? On one side of the graph. So if you are going to draw the partition, at 0 you have a vertical asymptote, and it goes to infinity. No critical points in between. The entire problem is one partition. Pick a test point, hopefully 1. You can pick any number. And then f prime at 1 is 1 over 1, which is equal to 1, which is larger than 0. So one single partition for ln, and it's increasing. Should I say, of course it's increasing? That's what it looks like. So answer, f of x is increasing on 0 to infinity. That's the entire domain. You can actually spell out is increasing on its domain, entire domain, whatever. But you can also just put this is much faster than spelling out all those words. So that is the first derivative test. If you need to write a sentence, write a sentence. First derivative test is used to determine intervals of increase and decrease within a function. And then as a side product, it gives us min and max, because right, these arrows are going to arrange themselves in some ways. So you know which way they follow each other, whether you have min or you have a max. The second part of this lecture is the second derivative test. Procedure is identical, except you will work off of the second derivative. So all of these steps that you see, let's say for this problem, we are going to do the same steps except off of the second derivative. And what we are looking for is concavity. So before we actually do problems, I need to tell you what the concavity is. Concavity. And then we'll go into second derivative with a subtitle. So what is concavity? It's related to the shape of the function. And I told you that something like this is concave up, and something like this is concave down. And when you have a piece that does this, there is a point at which the concave down part becomes concave up part. Now, if you want to challenge me and ask, really, these are concave up and concave down? Sure. Let me just do this. You see the upper part, right, above this point is concave up clearly, and it's concave down in this case. So you can have for concave up just these pieces. Like this piece is also concave up, and this piece is concave up. So those are concave up pieces. And if I just take this piece and put it on this side, they create the U shape if I connect them. So you can have the entire U shape or upside down U shape, or you can have the pieces. Now, why is concavity important? Well, let's pick on business again, because we can. Has a lot of good examples for this. And if you are going for business, guys, you have to understand these things, because this is where your work is. Business, economics, investments, all that kind of stuff. So what I'm going to have now are 3 portfolios that invested the same amount of money over the period of the same period of time. All right? So the first one, so let's say they all invest 10K, all right? So investors is putting in 10K. And I'm going to give you this, this, and this. This axis is time, and the y-axis is money. Which account portfolio or which accounts, portfolios, are making money in time? When you look at these three graphs, which portfolios are making money? All of them. Thank you. All of them. All three functions are increasing functions. So in time, all three portfolios are making money. But some of them make money faster than others. So which portfolio, one on top, two in the middle, three on the bottom, which portfolio is making the most money fastest? Yes. You do this, people. 2, 1, 3. Fastest, second fastest, worst. Now look at this one launching. A lot of money right there, right? Made in a short burst. And then flat, boring, 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 right? This one always constant, right? Look at that one. That's the exponential growth, right? We have that in our heads when we talk. Last night I had friends over mentioned exponential growth. He's not a mathematician, right? But he mentioned exponential growth. We haven't seen each other for 6 months, so he opened the door. Oh, Nick, you're growing exponentially. Well, first he saw kids, all right? So he thought, wow, you guys have grown, right? And then, oh, Nick, you grow exponentially too, right? Yes. So there you go. So now, this is the story of concavity. They're all increasing functions. They're all increasing functions, so they all make money. How fast are they making the money? Ah, that's the change of the first derivative, which is the second derivative, and we call that concavity here. So that's the concave up one, and that one makes money the fastest. That's the concave down one, and that's the most sluggish one. This one, concavity is a 0. It doesn't bend up, it doesn't bend down. So second derivative here is 0, right? If this would be the first derivative graph because, right, increase, right, stuff like that. So the concavity is going to show which way the first derivative, right, the increase and decrease, which way they change. So I'm just going to say over here, no concavity, concave up, and concave down. So these are the three cases. Now with that knowledge, second derivative test. So with that knowledge, we go into the second derivative test. So what's happening now? Well, we are going to do the same thing we did so far, except now we are going to have to do that off of the second derivative. So obviously the first function, x squared, right? Let's spice it up. X squared plus 5, because that really helps. So first example, oh, actually let me first write the rules. Before example, write the rules. So if the second derivative computed at point C, I forgot to put the word if second derivative computed at C, which is the test point, is larger than 0 on interval AB, that's the partitioning, then f of x is concave down on AB. If f double prime, right, the second derivative of f is less than, larger than 0 is concave up. There we go. If it's less than 0 on interval AB, which is your partition, then f of x is concave down. This is your second derivative test. The procedures, calculations, absolutely the same as the previous one. Let's go. Start with f of x equals x squared plus 5. Find the first derivative, which is 2x. We don't care about that one, but we needed to get to the second derivative, which is the one we care about. And that's 2. Second derivative is 2. This means concave up on the entire domain. And we know that it's x squared function. It's concave up. That's it. Next example, more interesting. F of x equals, say, let's go x cubed minus x because we can. So what do we have in this case? Let's see the first derivative. F prime of x is going to be 3x squared minus 1. Again, we don't care about this. We need the second derivative for second derivative test. So here we go. It's 6x. Second derivative is 6x. And this is the procedure. Now we can actually do something. So set the second derivative equal to 0, right? Solve the equation, you get x equals 0, and you get your point 0, 0. This point is known as inflection point. That's the inflection point. What is the definition for inflection point? Changes concavity. So critical points change, increase into decrease and other way. The inflection points change concavity. Changes concavity from up to down or down to up. So, okay, let's do the second derivative test. Partition. That's the first part. We have, again, at 0, we have negative infinity, positive infinity, right? It's the infinite domain. So once we did that, it's time to do the test points again. So always the same stuff. Test points, negative 1 and 1, it's fine. And this is second derivative test, so common sense, please plug it in a second derivative. So we have f double prime of negative 1 is going to be 6 times negative 1, which is negative 6, less than 0. I have concave down on that part. Concave down. Now we calculate the second derivative at 1, which is 6 times 1, which gives us 6, larger than 0, concave up. So it's concave up. And now I see that we can write the answer the same way. Function is concave up on the interval negative 1 to, sorry, 0, in negative infinity to 0. So answer, f of x is concave down on negative infinity to 0. F of x is concave up on 0 to infinity. Again, I never drew a function, I never did any of that work. I just know a lot about that function without actually knowing what it looks like. You can see that I can do off of this first derivative, I can do the first derivative test, right? And that's what 4.3 is. taking everything you learned so far in algebra, pre-calc, and calc, and do the 13 calculations, separate calculations, part A, part B, part C, part D, part E, part F. Right? You go through 13 calculations, and when you accumulate the points and intervals and everything, you are able to draw the function by hand. And that's what I said in 4.3, you get to graph ln squared of sine x. Right? You do that on a calculator to verify, you do it by hand, and these calculations are part of the list of things that you need to do. Right? So we know a lot about the function when we calculate these kind of things. So let's take, unfortunately it seems that we're not going to have time today for 4.3. So we'll have to march a little bit next time. I can probably squeeze in 2 examples more for second derivative test. And then I guess we'll call quits. So the first derivative test, second derivative test. This is a very long section in the textbook because, as you see, there is a lot of stuff that we can talk about. And, you know, calculations could be lengthy, equations could be annoying, right? So it's a lot of different things. Study page 256 from your textbook. This is what it looks like. So study page 256. See these visuals? They help a lot to put all of these concepts together. They show you that you can have a differentiable function if it's a smooth curve without asymptotes and spikes and cusps and things like that. Then they show you over here the increasing function, they show you decreasing function, then the first derivative test that you can have increase, decrease, and then there is a max in between, decrease, increase, and min in between. Here's the max, right, the horizontal, min, and there is your concavity. You see the way they draw, that's a concave up piece, and these are concave down pieces. And the inflection point, the blue one, is the one that changed from concave up into concave down in that particular example there. So, you know, study page 256, they have this amazing summary of everything we did today on one page. All right, let's pick some problems. So, concavity. Let's do the cheap problem, I guess, and then the evil problem, and that's that. So let's go with the concavity. How about problem 58? Generally, I don't like polynomials because we end up so many times with something we can't factor. And so f of x is equal to negative x to the 4th minus 2x cubed plus 12x squared. We're looking for concavity, so 2 derivatives immediately. So f prime is negative 4x cubed minus 6x squared plus 24x. And then the second derivative, the one we actually care about, is negative 12x squared minus 12x plus 24. Equal to 0. Now, before you freak out, factor out negative 12. And you see that that doesn't, then the calculations become a joke. So you x squared plus x minus 2 equal to 0. Now you can't set negative 12 equal to 0, so that just drops when you divide both sides by negative 12. So all you have to worry about is x squared plus x minus 2 equal to 0, which is easily factorable in x plus 2, x minus 1. From where x equals negative 2, x equals to 1. I have 2 inflection points. Two inflection points. And this is what partitions the space. So, second derivative test, partition. The first number is -2. The second number is +1. And we have negative infinity and positive infinity because polynomials have infinite domain. Great. 3 partitions, 3 test numbers. Let's go with -3. Let's go with 0, which is between, right, -2 and 1. And let's go with 2. Now, second derivative computed at -3. I'm going to use -12 times, and now I have -3 squared plus -3 minus 2. Observe that I chose the factored version rather than the actual one up there, because in a factored version I just need to know whether this is positive or negative and then times a negative number. We don't care about values of those numbers. We just care whether they're positive or negative. If you look at the definition here, right? They didn't say if the answer is -3, this is what happens. If the answer is -3.7, this is what happens. It's just if it's negative. So I actually don't have to compute at all. I can just go and make an argument over here that this is 9 minus 5, that's +4. Negative times positive is negative. I know this is less than 0 just by looking at it. I don't have to compute. Of course, you can compute and get the number. So the number for this is going to be -48. But we don't care that it's -48. We just care that it's negative. So the way I compute this quickly in my head is that's a 9, and these two are -5. 9 minus 5 is +4. I don't care about 4 anymore, because now I have a negative number type positive number, that's going to be negative. And that's the way I compute. But there is nothing wrong with, I mean, you're wasting time because you're getting the exact number. But there's nothing wrong on actually using a calculator or whatever to compute the whole thing. And when you get -48, you will still have the same conclusion as me. So we have a concave down on the first part. Now we go f prime, double prime of 0. That's again a -12 times -2, because zeros kill the rest. That's positive. So concave up. And the last one, second derivative computed at 2, the test point 2, is -12 times 2 squared plus 2 minus 2, and that's also negative because of these guys cancel, right? And you have negative times a positive. You have -12 times +4. That's a negative number. Again, concave down. Now you write your answer to the question. F of x is concave down on -infinity to -2 union 1 to infinity. F of x is concave up on -2 to 1. The question asked for intervals of concave up, concave down, concavity intervals. So this is the answer to the question. Everything up there is work, partial credit, and all that kind of stuff. That's the answer. One more problem, and we're done for the day. Next week, 4-3, 4-4, and we'll see if we can squeeze 4-5. The next two sections are long. Graphing by hand, I told you 13 calculations, then you draw the graph. And then the word problems on optimization. A lot of business and engineering stuff in there. Awesome stuff. You're looking for, again, min and max. So hopefully we'll be able to do even more than that. The last problem for today, something nice. Square root of x times ln x. That's problem 67. Concavity. Well, that's the second derivative. So let's go. First derivative is, it's a product rule, right? Right. So we have the product rule here. Copy the first times derivative of the second plus copy the second times derivative of the first. Fix it, fix it, fix it. Do not go and do two quotient rules now with the product rule and or whatever, right? Fix it, simplify. Observe that the first term is the square root of x over x, and the second term is ln x over 2 root x. You can make this into 1 over root x, right? If you divide top and bottom by root x, so the first derivative is 1 over root x plus ln x over 2 root x. Common denominator on 2 root x, and this is what we have for the first derivative. First derivative is 2 plus ln x divided by 2 root x. All right, this is a spicier version because obviously we have the more involved derivatives. We want the concavity, which means another derivative. And now we do the quotient rule. Square the bottom, you just get 4x. Then you have copy, 2x, times derivative of the top, which is 1 over x. Right, derivative of 2 is 0, and derivative of ln x is 1 over x. Minus, copy the top as is, which is 2 plus ln x, times the derivative of the bottom. That's going to be 2 over 2 root x. 2's cancel. So now fix this. Right? We need to go equal 0. Do not go equal 0 there. Simplify as much as you can, then go equal 0. Because we want to have the easiest possible equation to solve. Use the same trick on the first one. Right? You have 2 over root x. We already discussed that earlier. You have root x divided by x, so that's 1 over root x. So 2 over root x minus, and look what you have here. When you distribute this root x on both, 2 over root x plus ln x over root x. And these guys cancel completely. Over 4x. Well, that's cool. What I have is ln x over root x over 4x, and then they make it a double fraction over 1. So what's my second derivative? My second derivative is multiply 2 that are far apart, and that's ln x on top, and multiply 2 that are close by, which is 4x root x. You can write that x to the 3 halves if you want to. But we don't care. We don't care because when you set it equal to 0, 0 kills that denominator. That's why we simplified everything to a single denominator. When you cross multiply, 0 kills it. So you only have to solve the ln x equals 0. Convert that into exponential if you don't know logs. So that's e to the 0 is equal to x. So x is equal to 1. Yay! There's the inflection point. At 1. Now we go back and take a look at our problem to see other restrictions in a domain. So what is the domain of square root of x? And the answer is 0 to infinity. And what is the domain of ln x, it's 0 to infinity, but open interval. So now when I do my partition, I know that I am partitioning at 0 because I have a vertical asymptote there. Going towards infinity, I'm partitioning also at 1. That's the inflection point. So for the first derivative test, your partitions are critical points. For your second derivative test, your partitions are inflection points and asymptotes, right? So now what can I do? Well, I can put a half over here. Let me see. What is the where's the second derivative? It's right here, right? Okay, leave it. So a half, and then over here I can pick on. Let's pick e, because ln e is easy to compute. It doesn't matter what you pick. You just want to make it easy to compute. So second derivative computed at 1/2. Great. That's going to be ln of 1/2 divided by 4 times 1/2. Oh, I should have. I'm not gonna choose. I'm gonna change this. I want to use a quarter. So 1/4. Quarter is much better to calculate here, because you see that you have 4 times 1/4, and then you have a square root of 1/4. I can compute all of that stuff. I can't equally compute ln of 1/2 and ln of 1/4. It doesn't make it better or worse for ln, but it makes a hell of a difference for denominator. So I'm using a quarter. Now, if you know anything about logs, you know that this is ln1 minus ln4 divided by, this canceled, you have a half on the bottom. Now, ln of 1 is 0, and ln of 4 is blah, right? So you have a negative number divided by a positive number. That's less than 0. Concave down on the first part. I have no clue what the numbers are, and I don't care. I just know that ln1 is 0, and I am subtracting a positive value. 0 minus positive values. Now, sure, punch it in a calculator, you get exact decimals. You get decimals, and you can go from there. And now let's plug e. So second derivative computed at e is ln e divided by 4e square root of e. Well, ln of e is 1 divided by 4e to the 3/2. This is positive number divided by a positive number, which is a positive number, so concave up. Again, I did not bother looking for a calculator to compute because I don't care what numbers we get. All I care about is whether they're positive or negative, again, because the definition says, is it smaller or larger than 0? I don't care how much smaller or larger than 0. So now, write the answer. F of x is concave down on 0 to 1. F of x is concave up on 1 to infinity. And that's the end. That's the problem. So we're going to do more of these first and second derivative tests next class as a part of 4.3, because calculations within that section are these calculations and many others. All right, so I will see you next week. Bye.